All right, this tutorial is on section 8.1, similar polygons. We are moving into the similarity unit. Learning objectives for this section, use similarity statements. You're going to find they're very similar, no pun intended, to congruency statements with just one symbol difference. You can find corresponding lengths in similar polygons, and finding perimeters and areas in similar polygons, and then determining whether two polygons are similar. So, major core concept. Two polygons are similar if their corresponding angles are congruent and their sides are proportional. So think of similarity as same shape, but different size. So the shape means it's a triangle. They could both be right triangles, they could both be acute triangles, but the angles must be congruent. So in these two triangles, angle A is corresponding to D, those must be congruent. B to E are corresponding, those must be congruent. C to F, those must be congruent. But the size could be different, but the way in which all of the sides are different, they must be multiplied by the same number. So let's say that this side, little a, is a 3, and then this side is 6. It looks like it's being doubled, so that ratio needs to be applied to every other corresponding side of the two triangles. So the same number that you multiply to get up, or the same number that you divide to get down, must be the same. They're proportional. So let's look through our first example. So in this diagram, we're given this similarity statement. RST is similar to XYZ. So the similarity symbol is just your squiggly, no congruency with the equals underneath. We're going to find the scale factor between the two triangles. So find what number gets multiplied to get from corresponding side to corresponding side. We're going to list all the pairs of congruent angles. And then we're going to write a ratio of those corresponding sides. So looking at the scale factor. So let's look at our similarity statement first to determine which sides are corresponding. So these bottom ones, RS and XY, are corresponding. You look at your similarity statement. RS is the first two letters, XY is the first two letters. Those two go together. Then we're going to look at the actual measurements of those segments. You have 12 and 20. You reduce that fraction to get 3/5. Let's do the same thing with another pair of sides. We have YZ and ST. So it looks like 2 and 3 in both of our similarity statements. And those distances are 18 and 30. Reduce that all the way down and you get the same number, 3/5. Notice how these ratios are the same. And the last pair of sides, ZX and TR, those distances are 15 and 25. Simplify that to get 3/5. So these two triangles are similar because their sides are proportional. You set up a fraction, you set up a ratio, reduce it, and they're all the same. So that's the scale factor from RST to XYZ, 3/5. Now all the pairs of congruent angles. Well, it tells you in the similarity statement based on the order which angles are congruent and which ones are corresponding. So R and X are listed first. Those are congruent. S and Y are second. T and Z are third. Those are your pairs of congruent angles. Then because those ratios in part A are equal, and you have all three angles that are congruent, that would be your statement of proportionality, just listing these first ratios of your line segments of each triangle. So now we're going to look at determining what a missing value of a similar triangle statement would be. So we're given DEF to MMP in that order, and we're given that X is our unknown value on EF, and that's what we need to determine. Well, since we know that these two are similar, we're going to set up a proportion comparing two sides that we do know and two sides where one of them is the one that we don't know, because that's what we need to solve for. So we're going to pick 18 and 15, X and 30. Remember, one of them has to include the X because that's what you're going to solve for. If you want to use 20 and 24 as your first ratio, that's totally fine, but you must use X and 30 because that's what we're trying to solve for. Those are your corresponding parts. So set those up. There are a couple different ways you can do it. You could do 15 over 18 to x over 30, or you could do 15 over x to 18 over 30. Whichever way you decide to do it, your order needs to be consistent. So you can't compare 15 to 30 because they are not corresponding sides and you're going to different triangles. So we're just going to do MN to DE, which is just the purples first and then the greens second. So put those two together, substituting in the values. 18 over 15 equals 30 over x, and then we're going to solve this proportion using our cross product property. So 18 times x and 15 times 30 to get 450, and then divide both sides by 18 to get x equals 25. So if you wrote it where it was flipped, where 15 over 18 comes first, you then need to flip x over 30 to get your second one. So these could also work not only just for triangles, but for other four-sided shapes, and they also work for perimeters. So if the two polygons are similar, then the ratio of their perimeters is equal to the ratio of the corresponding side lengths. So remember that perimeter is the distance all the way around your shapes. Your ratio of your sides is the same as the ratio of your perimeters. So let's say we're looking at building a new swimming pool. An Olympic pool regulation size as a rectangular length of 50 meters long and 25 meters wide. So the new pool is going to have a similar shape, but instead it's only going to have a length of 40 meters. So we need to find the perimeters of both the Olympic pool and the new pool. So first, let's kind of unpack this problem. So we're given the length and the width of a rectangle and then just the length of the similar rectangle. So we have an x of the width of the similar rectangle that we don't know what it is. We need to find the scale factor of the similar rectangles in order to get the perimeter of the Olympic pool. Then we're going to use that perimeter to write and solve for a proportion to find the perimeter of the new pool that we're making. That's not the Olympic pool. Because those two pools are similar, the scale factor of the ratios is going to be the same for the lengths. So we've got 50 meters and 40 meters for our lengths. So 40 is the new one that we're making, 50 is the Olympic size. We're reducing that to 4 over 5 as our ratio. The perimeter of the Olympic pool is going to be twice that because in a rectangle you have two lengths and two widths. So that's 150 meters, or you can just take 50 plus 50 plus 25 plus 25 and you get the exact same thing. So then we're going to write and solve for a proportion to find the perimeter of our new pool. So the perimeter of the new pool is going to be x. That's what we're trying to find. And the perimeter of the Olympic pool is 150. And we are going to use our scale factor ratio that we determined from the lengths of the two pools of 4 over 5. Then we're going to use our cross product property and divide both sides by 5 to get 120 as the perimeter of our new pool. So you could also set it up as a scale factor with a decimal. You could take 4 over 5 and get 0.8 and then multiply that decimal by 150 to get 120. It's the same thing. So again, the perimeter of the Olympic pool is 150, perimeter of the new pool is 120. Let's double check that the ratio of the perimeters is equal to the ratio of the scale factor. 120 divided by 150, you can reduce that to 4 over 5. It's the same. Areas, though, are a little bit different. So the ratio of the areas is equal to the squares of the ratio of our corresponding side lengths. Remember, area is a squared unit. So whenever you're looking at the lengths of the ratio of the sides, you must square that ratio, both the top and the bottom, when you're comparing the ratio of the areas of the shape. So let's see what this looks like in action. Looking at these two triangles for a similarity statement, you're given one side is 10, one is 5. The area of this first one is 36 centimeters squared. Let's find the area of the smaller one. So we're going to set up a scale factor ratio comparing the two side lengths that we are given. Then we're going to write that proportion, comparing it with our areas, and then we're going to let the area represent the area of DEF. So setting up that ratio of AB over DE, 10 over 5. And then the area of our first triangle is 36. So we're going to plug all those pieces in. Remember, we are squaring the ratio of our side lengths. So you're going to square both the top and the bottom to get 100 over 25. And then using our cross product property to solve a proportion. 100 times a is 100a, 36 times 25 is 900. Divide both sides by 100, and your area of triangle DEF is 9. Remember, we have to use our units. We're given units of centimeters squared, so we need to do the same thing. Centimeters squared for triangle DEF. Okay, so now with more complicated shapes, let's just determine whether these are similar. So we need to find our corresponding side lengths and then write ratios to determine if all of them are equal. So A, B, C, D, E is the order. K, L, Q, R, P is the order of the second one. So K, L, and A, B is the order of the first pair of sides that we're going to look at because they are listed first in our statement. So KL is 8, AB is 8. That ratio reduces over 2 over 3, 8 over 12, sorry. Ratio reduces to 2 over 3. Then we're going to look at the next one. Numbers 2 and 3, LQ to BC. That is 6 over 9. Divide both by 3, and that reduces 2 over 3. So far, so good. If we ever reach a point where the ratio is not the same as the other ones, then they are not similar. So we got to keep going. Now we're going to look at QR and CD. QR is 4, CD is 6. Reduce that, you get 2/3. Still the same ratio. Now we're on to the next one, RP and DE. 6 over 9 reduces to 2/3. And the last pair, PK over AE is 8 over 12. That reduces to 2/3. So because all of our corresponding sides have a scale factor of 2 over 3, however, we do not have enough information to determine whether these two pentagons or these two polygons are similar. Remember, the two things you need for similarity, if we go back to the third slide, is we need all of our corresponding angles to be congruent and the sides proportional. Well, we got that all of these sides were proportional. However, we are only given one pair of angles that are congruent. If we were given that all of the other angles are congruent, then we could say that they're similar. But we don't have enough information to determine whether they are similar or not. Now, using dilations, you could be able to figure it out just based on the proportion of the sides, and then using that reflection over there. But you don't have enough information to determine whether any of those angles are congruent or not. So it doesn't necessarily mean that all the angles are congruent. You're only given that A and K are congruent. So you do not have enough information to decide if those two figures are similar.